Now, how does this preemptive version of shortest of first look like? The shortest remaining time first is an algorithm that will consider which process shall be running in the CPU each time a process enters the ready queue. If I am a process executing in the CPU and I need 6 time units, and a process entered the ready queue at this moment, and it needs only 4, and I have 6 this yet to go, and it needs only 4, I will be forced out of the CPU, and the one that needs lesser time will be allowed in the CPU. Here in this example, P1 arrived at time 0, it needed 8 time units. P2 arrived at time 1 and it needed 4 time units. P3 arrived at time 2, it needs 9 time units. P4 arrived at time 3 and it needed 5 time units. P1, being the first, will be allowed in the CPU. It will be running in the CPU for 1 time unit until P2 showed up. Now, P1 has been executed for 1 time unit and it needs 8 time units. That means 7 time units are left. Remaining time for P1 is 7, where the time P2 needs is 4, which is less than 7, definitely. So P1 will be forced out of the CPU and P2 will be allowed to run. At time 2, P3 entered the ready queue. At this moment, P2 was executing for 1 time unit. The remaining time is 3, while P3 needs 9 time units. Nothing will change. P2 will be allowed to execute until it finishes. It will be executing for 4 time units. It will finish at time 5. At time 5, in the queue, there are 3 processes. P1 that has actually executed for 1 time unit out of the 8. It needs 7. P3 needs 9 and P4 needs 5. The shortest is P4. P4 will be allowed in the CPU. It will run until it finishes because the other 2 definitely needs more than 5. Then P1 that now needs 7 and P3 that needs 9. Clearly the shortest is P1, so P1 will be allowed in the CPU. Then last will go P3. Average waiting time for P1, we have to calculate 2 waiting times. For its first time running in the CPU, it waited for 0 time. But it was forced out of the CPU and allowed again after how long? After he had gone 4 plus 5, that is 9. Okay, so it will have 1, it's 10. 1, okay, it's 9 and 1, so it will be 10. For P1, there will be 2 waiting times. For P2, P3, and P4 will be only 1 waiting time. P1 and it has 0, but then it waited until P2 and P4 executed. That is 9, so the waiting time is 9. And for P2, the waiting time for P2, the waiting time is actually 1. It's 0. It immediately entered the CPU. For P3 waited until all finishes execution. For P4, it waited until P2 finishes execution. Yet time 3, P2 أخذت 4, it waited for 1 time unit. The other way to choose from the processes is considering how important the process is. And who determined the importance of a process? Definitely the operating system. The operating system will give different processes different priorities according to how critical they are, or how important they are, based on what? For example, we can consider system processes more important than user processes. And we can consider that there are processes that are time sensitive. These are more important than processes that are not time sensitive. These are, for example, a process that belongs in the مثلا في السيستم بتاع الفاكولتي. A process that belongs to the dean's office is more important than a process that belongs to the student lab, for example. So priority scheduling is one of the commonly used scheduling algorithms that based on the priority of the process that is given to it by the operating system. There are two types of priority scheduling: preemptive scheduling and non-preemptive scheduling. In the non-preemptive scheduling version, a process, if the process was in the CPU and a process of a higher priority arrived in the ready queue, the process will continue execution until it finishes. In the preemptive version, if a process was running in the CPU and a process with a higher priority arrived in the ready queue, the process in the CPU will be forced out and the one with the higher priority will be allowed in. We can look into shortest job first as a priority algorithm if we consider in a priority is given by the time of execution. The problem with the priority scheduling is that processes with low priority will be not allowed in the CPU and will be waiting for long times, causing them to starve. We call this starvation. And a joke that is told in operating system books that when they changed a mainframe in Yale in 1983, they found a process waiting in the queue since 1976. That's a joke, okay. But that shows you that priority can create a huge deal of unfairness for processes with low priority. To handle this, we use what a process that calls aging. Aging is a fix for starvation by increasing the priority of a process as it waits. The longer it waits, the higher its priority becomes until it reaches a priority level that will allow it into the CPU. An example for priority scheduling: assume we have 5 processes with different priorities. P1 with priority 3, P2 with priority 1, P3 with priority 4, P4 with priority 5, P5 with priority 2. The priority indicator, sometimes uh, you have to read the problem well, because sometimes the smaller priority is the higher priority, and priority 0 is the highest one, and and sometimes priority is the as increases with the number given, and priority 5 is higher than priority 1. Here clearly, the smaller the number is, the higher the priority is. So priority 2 was allowed first, then priority 5, process 2 was allowed first, then process 5, then process 1, then process 3, then last came process 4. I'd like you to solve this again, taking into consideration arrival time and using preemptive priority scheduling. Try to practice as much problems as you can. It will help you in your exam.